1 squared is 1. 1 minus 1 is 0. Cosine of 0 is 1. This whole term goes away, and we're left with just the amplitude. So in that case, if B is equal to 2m omega naught, we don't have any oscillations at all. Even though this is a damped harmonic oscillator, if we have this exact value for the dampening constant, then we don't even get any oscillations. What happens is, we have our mass at the end of the string. You imagine, this is difficult to visualize with air, but imagine that mass was in some fluid, say water, and then we let it go, and then it just moved to its equilibrium position and slow down and slow down and slow down and slow down. It never moves past the equilibrium position, therefore it never oscillates, and that's because if we have this critical value for the dampening constant, right, that essentially means that resistance of the fluid to the motion of the mass is going to just about cancel out any forces that were due to the Hooke's law constant. So they're exactly in balance, so it just decays down to its equilibrium position. Right? Another possibility, so this is called critically damped. Okay? Because the damping constant is equal to its critical value. Now, if we have, so this is B equal to BC. If we have B less than BC, we have underdamped, which is the type of oscillation we saw before, right? If you imagine that I take that mass and that spring out of the water, and now it's in air, and now I pull it back, and now it oscillates like normal, right? It still slows down because the air is still resisting that motion, but it's not at the exact value for that thing to just slowly come to rest, right? Now, so this is underdamped. Okay. And the last one is, well, what if, okay, so B less than BC. What if we have the last case? BC is, or B is greater than BC, right? If B is greater than BC, well, I get some number bigger than 1 here. I square it. I have 1 minus some number bigger than 1. I have a negative number. I take the square root of a negative number. Okay, at first you might think, well, I then have imaginary positions for the position of the oscillator. Well, no. Remember that I can have, I have a definition, right, of sine and cosine in terms of exponential functions, right, our Euler equations. So if we stick an imaginary number inside of theta here, right, I have an imaginary number inside of theta here and theta here, so then I have a real number times two imaginary numbers. Those imaginary numbers multiply together and give me a negative number. So this guy here really just turns into another, oops, shouldn't be an I there. This cosine function turns into something like an exponential function, right? Because I'm ending up with real numbers in these exponents instead of imaginary exponents if theta itself is imaginary. So what this means is that I have now an overdamped situation. And an overdamped situation is like a critically damped situation, except that decay happens more slowly because we have another multiplication by an exponential function, which that exponential function, that couple exponential functions that are inside here will be multiplied by this exponential function. So that's going to reduce essentially that time constant. So this is overdamped. So beta greater than beta critical, or B greater than B critical. Okay. So now imagine that I'm taking that same mass on a spring, right, that I've put in the water, and I took it out and put it in the air, and now I'm going to put it in a tank of molasses, and I stretch it out and let it go, and yeah, that spring's gonna cause that thing to slowly move back towards equilibrium, but it's resisting the viscosity of the molasses, so it's going to happen really, really slowly. Okay, so we see three distinct regimes of physical behavior depending on how these constants interact, right? Given by our differential equations. So this is sort of an interesting situation where just with some math, we can predict that a physical system can have three distinct states, right? If this were, we were talking about how individual atoms moved around in a substance, these would be different phases, right? Liquid, solid, gas, right? They're not analogous, obviously, right? But we see that same sort of phenomenon, that the same system produces completely distinct behaviors depending on what those values are, okay? Again, we're running a little, well, no, not too much, too short. So again, class is ending a little bit earlier. Maybe I'll be able to upload this in one video, which would be handy. So we'll have one more class, right? We'll have our last lecture on Wednesday, and during that lecture, we will talk about what I hope is kind of something interesting, which is musical tones, right? We're talking about oscillations, essentially vibrations. How does this generate music? Well, we'll see that next class, right? If you pluck a guitar string, what tone is produced, okay? So we'll do that next class, so that will be Wednesday's class. Friday, I will email around a practice final, and then on the following week you will have your final. I have not exactly decided how the final will work. I don't think it'll be very much different from the way I've been doing or have done the exam since classes stopped meeting in person, but we'll see. I'll let you guys know about that pretty soon, but I'm just waiting on a couple things. Okay, hope everyone is still doing well and that you're not too overwhelmed, and you know, if you're feeling a little stressed out, just a couple more weeks and the semester's over, right? Okay, so all the best. Talk to you soon.